Hello, everyone. My name is Nick, and I'm going to walk you through my final project for the Duke AI product management course. So, in our final project, we were given this data set right here on the left. There's about 9,500 entries um, with a target variable right here, the PE, that we're trying to predict based on the inputs we have from A, B, C, and our columns A, B, C, and D, the temperature, exhaust vacuum, ambient pressure, and relative humidity. So for my approach, I split the data into two groups. Training data, which had about 80% of the data, or 7,600 records, and then the other 20% I'll use for test data to measure the models that I create to see which one might be more accurate. Um, so that's what I did. I split the data up. And so, first, using the training data, I wanted to see how each individual input correlated with the output or the target. So as you can see in these graphs, when I graphed them and added a trend line and pulled up the correlation, temperature and exhaust vacuum both had pretty high correlations of 0.89 for temperature and 0.75 for exhaust vacuum, but ambient pressure and relative humidity were quite a bit lower at 0.14, 0.25. So for my models, I decided to build two models, one linear regression model with temperature and exhaust vacuums as the only inputs. And then as my final model, I decided to include all inputs just to see, even though these have quite a low correlation, they still might explain some of the outputs we have on the target. So I wanted to see how linear regression would perform with the two high correlated inputs and then all of the inputs all together. So on my first linear regression with those first two inputs with the high correlation, this was what the output I got in Excel after running linear regression analysis. An R square valued of 0.91, and then these were my coefficients, and my converted that into the formula I would get for the two input model for linear regression. And on the four input model, I did the exact same thing, got a slightly higher R squared value, and got the following coefficients in this formula. The higher R squared value made me think this might be a better model, but we need to see if there's any overfitting. So that's why we still have training data. So I will show you my model comparison on the last page. Yeah, so I took the two models, took our test data that we had back on the original sheet that we split out, the 20% that we didn't use to train any of our models, and measured what the actual prediction would be based on the first model with two inputs and the second model with all four inputs to get our prediction. And then I measured our error and error squared and absolute error to try to determine how these models are performing. So with those values, I was able to calculate the mean squared error as well as the mean absolute error for each model to show that I got 23.6 and a 3.8 for our first model with just two inputs. And then on our second model, we got a mean squared error of 19.6 and 3.5. So since the mean squared error and mean absolute error were lower on our second model, shows that this model is actually more accurate and a better fit for the data and better predictor of the net hourly electrical energy output than the first model that only used the two inputs.